Welcome to the last lecture of CMPT 726 Machine Learning. Last time we discussed support vector machines, so we continue our discussion on support vector machines. And in particular, we looked at the soft margin SVM. We did that by starting with the hard margin SVM, which is the kind of the vanilla SVM, and we changed the constraints and then reformulated the optimization problem into an unconstrained optimization. And from there, we looked at the loss function and we noticed that this is actually kind of part of a general form of loss functions. From there, we compared three different loss functions. One of them is the 0-1 loss, which I guess the 0-1 loss is ideally the loss function that we should use. However, optimizing it turns out to be NP-hard. So the hinge loss is actually a surrogate loss for the 0-1 loss, which is effective at the classification task. We also compared the hinge loss with the square loss, and basically, as expected, because the square loss is more designed for regression, it doesn't really work that well for classification. And we saw the geometric interpretation through a graph of why this is. Then we began talking about logistic regression. In particular, we introduced the cross entropy loss. So that's where we'll begin today. So just a very brief recap on this slide. So in logistic regression, we have a model where it's basically based on a sigmoid function sigma. So sigma of W transpose X, if we evaluate, so after training the model, if this evaluates to more than 1/2, we predict 1. And if sigma of W transpose X evaluates to less than 1/2, then we predict -1. This is actually equivalent to predicting 1 whenever W transpose X is greater than 0 and -1 when W transpose X is less than 0. So the decision boundary is actually X such that W transpose X equals to 0. So all of this is actually exactly the same as the SVM. So the decision boundary is the same, it's the hyperplane. And so logistic regression is also a linear classifier. So where logistic regression differs from SVM is that we're going to be using the cross entropy loss. So here we show it with L2 regularization. So the loss function is basically minus sum of this indicator of yi equals to 1, log probability of y hat I equals to 1, plus indicator of yi equals to -1, times log of probability that y hat I equals to -1, plus regularization. So this Iverson bracket is basically equal to 1 when the insides are equal, and 0 otherwise. So sometimes I call this the indicator function. So we looked at an example of a data set in red and blue here, and then an example of training, kind of optimizing this loss function using iterative optimization methods. And we can see the decision boundary change with every iteration of the optimization algorithm. So that's basically where we left off last time. So today we're gonna continue. Let's first take a look at why this loss function is called the cross entropy. So remember that previously we discussed the entropy h of y, right? In this case, h of y hat. So suppose that y hat takes only on values 1 and -1. Then we can actually compute the entropy of y hat to be as follows, just plugging into the formula for entropy. It's going to be sum over a negative sum over all the possibilities of y of p of y log p of y. So basically when y can only be 1 and -1, this is equal to p of 1 log p of 1 plus p of -1 log p of -1. Okay, so that's entropy. Cross entropy is something that we haven't talked about yet, but it's actually very similar to entropy. The main difference is that this expectation is taken over another distribution Q, not the same distribution P here. So basically the formula just involves negative sum over Q log P instead of P log P. We can also write that out as well. So if you look back at the loss function, we know that for every data point, the label is either going to be 1 or -1. So in every term of this sum, only one of these terms that we're adding together is going to be 1, right? So for example, if the label is 1, then yi equals to 1, this indicator function part would evaluate to 1. And then the other indicator function, yi equals to -1, that evaluates to 0, so you don't get the second term. So every term of this summation will only contain one of these. And because of that, you can think of the cross, because of this, this basically means that for the cross entropy loss, it corresponds to choosing a Q of y, which is equal to 1 if y equals to 1 and 0 otherwise, or the other way, 0 if y equals to 1 and 1 otherwise. Right? So if you make this choice, we can see that in every term of the sum, one of these will be 1 and the other will be 0. So let's start from the loss function and simplify a little bit and see what we get. Okay, so let's start by writing down the loss function, the cross entropy loss. So it's going to be negative sum over all data points of the indicator of yi equals to 1 log probability. So I'm just going to write p over here for probability that y hat I equals to 1 plus the indicator of yi equals to -1 of log p y hat I equals to -1. Okay, and then I guess here we're going to be using the regularized version with L2 regularization. So now I'm going to do a few steps of algebra just to simplify things a little bit. So first, still sum over all data points. So first, we're going to actually write down what the probability that y hat I equals to 1 is. So remember that y hat I, the probability that it equals to 1 is actually given by sigma of w transpose x, xi, right? So remember this. So now we're just going to write sigma of w transpose x I instead of the probability that yi equals to 1. Okay, plus indicator of yi equals to -1 times log. So here we have probability that y hat I equals to -1 because y hat I can only take on two different values. This is actually just going to be 1 minus probability that y hat I equals to 1. Right? So we can directly write 1 minus probability that y hat I equals to 1, which is just going to be sigma of w transpose xi. Okay, do I have one more bracket? Yes, I do. Okay, and then plus lambda 2 norm of w squared. So next, we're going to plug in what sigma is. So sigma is the sigmoid function. So again, a summation of indicator of yi equals to 1 times log. So now it's going to be the sigmoid function, which is 1 over 1 plus e to the power of w transpose xi. Plus indicator that yi equals to -1 of log of 1 minus this thing. So 1 minus the sigmoid. Okay, so one more close bracket for the summation, and then plus our regularization term. So we're going to simplify this a little bit. I guess most of it is looks pretty nice already, but we're going to work on this part a little bit. So 1 can be written as 1 plus, so this part can be written as 1 plus e to the minus w transpose xi over 1 plus e times w transpose xi, right? I'm just putting everything into common denominators, and then minus 1. And the 1 and the minus 1 will cancel after you do this. Okay, so now, just so we have a bit of symmetry, because over here we have 1 over, but here we have something that is not 1 over. So we can actually make this, we can actually multiply top and bottom by e to the power of w transpose xi. And then the numerator will become 1. And the first term of the denominator will be e to the power of w transpose xi. And then these two will cancel out and give you a 1. Okay, so inside the log, so now we have finished simplifying inside the log. Let's just write that down, write down the results. So indicator that y equals to 1 of log, so nothing changes here, 1 plus e to the power of minus w transpose xi, plus indicator that yi equals to minus 1 of log of 1 plus, and this time e to the positive w transpose xi. Okay, and then the bracket for the sum plus our regularizer. Okay, so just a few more steps and then we should see something interesting. Actually, we'll just get the same result that we saw a few slides ago. Okay, so what we're going to do is to notice that when you have log of 1 over something, which appears in two places, you can write that as negative log of the reciprocal. And that negative sign will then cancel with the negative sign in front. So now we no longer have a negative sign in front. We just have sum of yi equals to 1 times log of 1 plus e to the minus w transpose xi plus yi equals to minus 1 indicator of log 1 plus e to the power of w transpose xi. Positive power this time. Summing all of that plus regularization term. I guess I probably shouldn't have kept the regularization term along. Just a lot more writing this way. Okay. And finally, we're just going to make an observation. So let's take a look at each term of the sum, right? Each term of sum. When yi equals to 1, we have, well, when y equals to 1, the second term is gone because the indicator is 0, right? And then the first one is going to be 1. So we just have log of 1 plus e to the power of minus w transpose xi. And when yi equals minus 1, the first term is 0, and the second term, we just have the log part. And of course, the only difference is that the power here is positive instead of negative. Okay, so turns out that we can simplify this even more. remember that the probability is given by the sigma of W transpose X expression over here. But actually the logistic regression is very similar to SVM in the sense that when W transpose X is greater than 0, we predict one label and we predict the other label otherwise. So you can think of W transpose Xi as equal to Y hat, right? So then if we think like that, then this is actually 1 plus e to the power of minus y hat I. And then the second case is just going to be 1 plus e to the power of y hat I, right? If we call W transpose Xi as y hat I. And we're going to do this just to draw a parallel to SVM and the other loss functions that we have discussed so far. So if you now stare at these expressions that are underlined for a bit, you will notice that, okay, so now this is actually just equal to log of 1 plus e to the minus y hat I. Because when yi is equal to 1, we get exactly this. When yi is minus 1, the minus 1 cancels with the minus, and we get exactly this expression. Okay, so this is basically same as logistic loss, or what we called logistic loss, I think 2 classes ago, or maybe it was last time. Okay, so finally we have shown that if we plug in the logistic loss, then so instead of let's say the hinge loss or the square loss, if we plug in the logistic loss, then we actually get logistic regression. Taking a look at this again on the slides. So we began by writing down the loss function, the cross entropy loss with L2 regularization. So the first thing we did was actually notice that because yi can only take on 2 different values, y hat I equals to minus 1 is the same thing as 1 minus y hat I equals the probability that y hat I equals to 1. Next, we simply plugged in our model, which is that the probability that y hat I equals to 1 is equal to sigma of W transpose Xi. So therefore, this part just becomes 1 minus that. So every line we're just changing a little bit. Next, we plugged in the function sigma, which is just 1 over 1 plus e to the power of negative the argument of sigma, which is W transpose Xi. So we did that in both places that sigma appears. Okay, next we simplified this expression a bit by putting everything into common denominators. We get a 1 plus e to the power of minus W transpose X, and the 1 cancels with the original 1 here, leaving us with just e to the power of minus W transpose X, Xi. To make things look a bit nicer, we multiply top and bottom by e to the power of W transpose Xi, positive exponent, and that makes the numerator 1, and the denominator basically the minus power gets cancelled. That gives us the 1, and the 1 multiplied by this e to the power of W transpose Xi gives us the second term in the denominator. Okay, on the next slide, we copy the result from the last line on the previous slide here. And we basically simplify log by taking the reciprocal of the inside, which pops out a negative sign for both of the logs, and the negative sign cancels with the negative in front. And in the end, we get this final expression over here, which is sum over data points of yi equals to 1 indicator times log of 1 plus e to the power of negative W transpose Xi. Okay, and then plus the other case for yi equals to minus 1 indicator times log of 1 plus e to the power of positive w transpose xi plus our L2 regularization term. So then we made some, I guess, keen observations where w transpose xi looks like y hat. So we're going to replace with that. And then because yi equals to 1, when yi equals to 1, only the first term appears. And when yi equals to minus 1, only the second term appears. This sum can only be one of these possibilities. And that basically allows us to simplify the loss function into log of 1 plus e to the power of minus y hat. So originally, when we introduced the logistic loss, we had a log 2 here, but actually the dividing by log 2 is just a constant, and that doesn't really matter. So it's really just a matter of the definition of what the logistic loss is, right? Even if you didn't have the log 2, it doesn't really change the optimal parameters. Okay, so now we have another function, which is a function of y hat. So I guess all of this simplification is really to put the loss function into this form, a function of y hat. So we can actually compare with the 0,1 loss, the hinge loss, and the square loss. Okay, I guess we'll take a look at that soon, but this loss function is actually, there's no closed form solution for it, so we will need to use iterative gradient-based optimization methods, like the gradient descent. Well, the good thing here is that the objective function is actually convex and also Lipschitz continuous. So we know that using iterative gradient-based optimization methods will eventually allow us to converge to the optimal parameters. Okay, so everything we talked about so far is actually for a linear decision boundary. If we wanted to separate data that cannot be separated using linear decision boundary, then we can take the same approach as SVMs and use features. So basically, instead of x, we're going to replace x with phi of x. The only thing is that with that replacement, that's all we can do. There's no further simplification of the features into something like the kernels, right? So the kernel trick no longer works here. And that means that if we replace the features, if we replace the raw data points with features that are very high dimensional, then computationally speaking, that may not be so favorable. Okay, so in this case, what we typically do with logistic regression is to learn the features instead of picking features. And we know that whenever we start talking about learning features, we're really talking about a neural network model. And it turns out that if you do logistic regression with a neural network model, it's actually the same thing as using a neural network whose output layer has sigmoid activation. So the upside here is that obviously your model is much more expressive. You will be able to have nonlinear decision boundaries. However, because the model has now changed to a neural network, the objective is no longer convex. Okay, but then again, we don't really have any constraints still, so we can still use iterative gradient-based methods to optimize the loss function, even when the model is a neural network. So then we would be able to separate data sets like this, right? Maybe a ring representing class from kind of representing one class, and then an inner ring representing the other class. So if you do this, I guess we have seen this a little bit in the neural network playground by TensorFlow, I think maybe 2 or 3 weeks ago. Here's another very similar animation. So we're just training a neural network to classify the data set, and after a while we get this triangle shape as the decision boundary. Maybe we can look at it again. Initially, the training doesn't change the decision boundary very much. In fact, we can't really see it here, but after more iterations, slowly we get a nice decision boundary like this. Okay, so now finally, let's talk about comparing the logistic loss with the other three loss functions that we have discussed before. So here, just to remind you, the 0,1 loss in blue is probably ideally what we want to use, but optimizing that is NP hard, so we can't do that. So instead of doing that, we have to use surrogate loss functions, and three of them are plotted here. The square loss in magenta, that one we know doesn't really work too well because we're over penalizing many of the data points, right? Even the correctly classified points will be penalized. Same with the 2 incorrectly classified points. The hinge loss from SVM was much better, and that was in green. And if you overlay the logistic loss, it's actually shown in orange. So the behavior is quite similar, actually. We get some penalty for points that are not, I guess, very correctly classified over here. And then for the points that are too incorrectly classified, we do get some increasing loss that is a bit faster compared to the hinge loss. But actually, it's not much faster. This asymptotically, this part will actually approach a linear curve, right? So it's just gonna go up linearly, and same on the right side. It's gonna approach 0. So the behaviors are actually very, very similar. So when do we use which one? So the hinge loss can be formulated as a constraint problem, and then we did all this math for SVMs to show that once we can derive the dual problem, it only involves inner products between the data points, and that means that we can use the kernel trick. So I think the key benefit of the hinge loss or using SVMs is that you can use the kernel trick. Well, what's so good about the kernel trick? If you use the kernel trick, you can actually use very, very high dimensional features, even infinite dimensional features, without making the problem computationally intensive, right? Because the kernel only involves xi and xj, even if phi of xi, xj are infinite dimensional. When we use the unconstrained problem, it doesn't actually work that well with iterative gradient-based methods because the derivative is actually discontinuous. I think it should actually work not too badly, but not as well as the logistic loss. The logistic loss can only be formulated as an unconstrained problem, so we must use iterative gradient-based methods to solve it. As we also discussed, we can't really use the kernel trick. That's because the resulting model doesn't only involve the inner product between the data points. Okay, but so instead of using the kernel trick, we tend to use neural network models so that we can learn the features instead of picking the features. Okay, so let's continue. So we're almost done the entire course. So we're going to talk about Softmax classification. So this is basically the generalization of logistic regression to multiple classes. Sometimes it's called Softmax regression, even though that's kind of a misnomer because this is really classification. Sometimes it's called multinomial logistic regression or multinomial logit, right? Probably we'll go with Softmax classification here, but you should know what these mean when you see them. I'm going to go through this quite quickly. So suppose we have k classes. The model for Softmax classification is going to be a function that takes as input the data point, and it will output a vector of probabilities for each of the classes, and each of the probabilities is going to be given by the functions f1 to fk, where the f function is always going to be in the numerator exponential of kind of wk little k transpose x, and then in the denominator you basically add up all of these exponential w transpose x terms summed over every index. So basically this makes sure that all of these probabilities add up to 1. The parameters are going to be wj vector, and then j goes from 1 to capital K. So this function It's actually called the sigma of, it's also called a sigma function or the softmax function, except that we plug in a vector z instead of a scalar. And basically when we plug in a vector z, every component will just be exponential of zk over sum of the exponential of z's. So this is a softmax function. So we're not going to get too deep into it, but here's one example. So here's basically writing down the cross entropy loss for this model and then optimizing it using iterative gradient-based methods. So here we can see kind of 3 decision boundaries. One of them is separating green from blue. So this one is separating green from blue. This one is separating red from green. And finally, this decision boundary is separating red and blue. Okay, but overall, the decision boundaries look like this. So everything here should be classified as red, everything here blue, and everything here green. Okay, again, to train a model, we use the cross entropy loss, right? Sometimes called the multinomial cross entropy loss. In machine learning, people just say cross entropy loss because very often we have many different classes, not just 2 classes. So here we're going to be showing the L2 regularization version. It's actually very similar to the cross entropy loss in the case of 2 classes. In the case of 2 classes, maybe one slide before. So in the case of 2 classes, we sum over the data points, and in each term of the sum, so for each data point, we have 2 terms we add together. But really, this is always going to be one term, right? Only one of the terms will be non-zero for any of the data points. So the idea is quite similar for the softmax classification. So for the multinomial cross entropy loss, instead of summing 2 terms, we're summing k terms. Each of the k terms has a yi equals to k indicator. Again, yi can only be one of the classes. So for every I, only one of these k terms will be non-zero. Okay, and then we add them all up. For the L2 regularization, we have to regularize every vector, wj. So this is kind of like, if you think of all the vectors wj stacked up as a matrix, then this would actually be the Frobenius norm. So hopefully that also reminds you of weight decay for neural networks, right? So we kind of talked about that as well. So now doing the same exercise as what we did here, but then now I'm going to skip most of the steps. Basically, we write down the loss function, we do the same kind of simplification, and the end result will actually be something that looks like this. It will just be negative sum over data points, sum over classes of indicator yi equals to k, and then you have this wk transpose x term minus log of sum of exponentials. Okay, so this form is actually easier to compute numerically. You can kind of see that when we take the exponential of things, the numbers can get very, very big. And then when we sum and log, sometimes the results are not very accurate if you compute these directly. But there are many algorithms and routines for accurately computing the log sum exp function. Okay, so in this case, doing the math, so previously we did the math here to show you guys a comparison between the hinge loss and the other loss functions with the logistic loss. For the softmax classification case, by doing some math, we'll be able to obtain an expression that is going to be easier to compute, more accurate to compute numerically. So when k equals to 2, softmax classification is equivalent to logistic regression. So if, I encourage you guys to try to show that, right? So write down the loss function as well as the model for softmax classification. And then hopefully you should get the same thing as logistic regression. Again, there's no closed form solution for the optimal parameters, but again, the objective function is both convex and Lipschitz continuous, provided that we're just going to be plugging in W transpose X over here, right? If we start to replace X with a feature, a learnable feature, and then doing all of that to make this W transpose X a neural network, then again, it becomes a neural network with softmax, with a sigmoid activation at the end of the last layer. And then again, in that case, the function will not be convex anymore, right? But in either case, we can use iterative gradient-based optimization methods to find the optimal parameters. Okay, so hopefully this gives you some basic idea about softmax classification and logistic regression, and kind of the commonly used neural network architecture with a softmax activation or sigmoid activation at the last layer, which is actually equivalent to doing softmax classification with a neural network inside the exponential. So the last thing I want to touch on is class imbalance. Sometimes there are many more examples in one class than in the other. So this is known as the problem of class imbalance. This is actually very, very common. Usually when you want to classify something as good or bad, in real life, something bad might occur much more rarely than something good, right? I know it's a bit abstract. I mean, one example could be COVID testing, right? Hopefully most people are going to test, in that case, negative, and then everyone else is testing positive, right? But only a very small percentage. So in situations like this, a classifier that is really stupid, for example, always predicting whatever label occurs more frequently, will actually achieve a very, very good accuracy. So this is kind of a something that this means that we cannot just use the original objective function that we saw. If we use the previous objective function, then the rare class will contribute very little to the overall loss, right? If we care about all classes equally, then we can always reweight the classes in proportion to the inverse frequencies. Basically, the more frequent the class occurs, we will weigh that class less, and the weights are basically given by this expression. So we have n data points in total, and then we divide by k times the number of times that the number of data points whose label is k. So this actually wraps up all the course material for CMPT 726 machine learning. So hopefully you guys have learned a lot. We're now going to take a 10-minute break, and when we come back, we're going to summarize the course. Okay, then let's do a high-level view or a bird's eye view of the entire course. Starting with the very beginning, why machine learning? So AI is hard because the inner workings of our brain are not well understood. Even though we're able to convert input to output correctly, we don't necessarily know how our brain does it. So we can't really write a program to do so. So, however, even though we don't know how our brain converts input to output, we know what output should be for every input. So we can use this knowledge to teach the machine. So the goal of machine learning is to predict outputs from inputs. Okay, so a review of the general machine learning principles that we have talked about. So the general framework in machine learning is given a data set of input-output pairs, we would like to predict the output corresponding to an unseen input. And the way we achieve this is to first devise a model. And we have seen several different kinds of models. And the model basically takes an input and produces a prediction. Next, we devise a loss function, which measures how good the predictions are compared to the target output. And then we train the model. And by training, we minimize the loss function with respect to the model parameters in order to determine the optimal model parameters. And finally, after training, we test the model. And testing means we use the model with the optimal parameters determined from training to generate predictions on unseen inputs. Okay, so now let's take a look at each of the steps. First, devise a model. So we talked about two kinds of models, deterministic models and probabilistic models. In the deterministic model, given an input, we produce an output. And in the probabilistic model, given an input, it produces a distribution over possible outputs. So the example of the deterministic model is the simple linear model here. We have seen other ones such as the neural network, the multi-layered perceptron. For the probabilistic models, the output is actually a distribution. For example, a normal distribution with a mean of W transpose X and a variance of sigma squared. Okay, so back to the general framework. So after we have devised the model, we have to devise a loss function. And we have seen several different ones. So for deterministic model, the loss function can be any function that assigns high values to incorrect outputs and low values to the correct outputs. So we have seen, for example, the square loss in linear regression. For probabilistic model, we looked at maximum likelihood, and the loss function is actually the negative log likelihood. And we also looked at maximum a posteriori, and the loss function is the log posterior, the negative log posterior. Okay, and then we have also shown that these loss functions with probabilistic models actually correspond to exactly to the square loss and also the ridge regression loss for the deterministic linear models. Okay, so now, again, bird's eye view, we're going to move on to the training the model. So training involves finding the model parameters that minimizes the loss, and we have seen several different approaches for doing this. The first approach we saw, which was in ordinary least squares, ridge regression, and so on. So the way we trained those models was to set the gradient to 0 and solve for the optimal parameters analytically. Sometimes that's not possible. In that case, there would be no closed form solution for the optimal parameters. And then we had two cases. If the optimization problem is unconstrained, we can use iterative gradient-based optimization methods. Right? So an example of an unconstrained optimization problem was the minimization of the square loss. In this case, if the loss is convex in Lipschitz, then we're guaranteed to find the local minimum. If the loss is non-convex but Lipschitz, then it may get stuck in local minimum and the gradients may vanish. And then we also saw some examples where the loss function is even non-Lipschitz, and here the gradients may explode, leading to divergence. So that was the unconstrained case. And for most of the course, except for SVM, we were looking at the unconstrained case. With SVMs, we looked at our first constrained optimization problem. And to solve these problems, we can check if the Slater's condition holds. And if it holds, then strong duality holds. So then we can choose to take the dual or to derive the dual problem and try to solve the dual. Sometimes, as in the case of soft margin SVM, we can actually do some algebra to reformulate the problem into an unconstrained problem. If this is not possible, then we can still use dedicated solvers when the objective and constraints are of a particular form. So for example, if we have linear constraints and quadratic cost, that would actually be a quadratic problem, a quadratic program, and then there are many different solvers for those. So we only kind of touched on optimization. Normally that would be an entire course, and we actually do offer an optimization course. So if you're interested, definitely check it out. Okay, so that was training the model. Lastly, we have to test the model. And in testing, in many cases, we take the model's output directly as the prediction. So that's basically what we do when we do regression. With classification, after the model predicts something, we still have to do some kind of post-processing to obtain the class that we predict. And we basically looked at thresholding as a way of coming up with a class after obtaining the model output y hat. Right? So if you recall, for SVM and logistic regression, whenever W transpose X is greater than 0, we predict one class. And whenever W transpose X is less than 0, we predict the other class. So that's kind of the general picture for the machine learning framework. And then we delve into a bit of details with some parts. For example, one of the parts is model selection. So often we have a family of related models which differ in hyperparameter values. So for one example is, let's say, polynomial models. So that's basically a family of related models that differ in the degree of the maximum degree, the term with the maximum degree. So in this case, the previous machine learning procedure becomes the inner loop. And then we repeatedly perform all of those steps in an outer loop, which selects the model. And in model selection, we would like to minimize the expected error on an unseen example. And we delved a little bit into the theory here and talked about the bias variance trade-off. And basically the expected error, which is what we want to minimize, is actually can be decomposed into three parts: the bias squared, variance, and also irreducible error. The bias refers to the difference between model predictions when trained on the unseen examples in the target output. And the variance refers to how much the model prediction varies when trained on different data sets. In general, more expressive models, the models with more parameters in general, can achieve low bias, so they can fit the training data better. And the less expressive models can achieve low variance, which generalizes to unseen data better. So we have looked in great detail the example of the polynomial model up to degree 20, right? So degree 20 model had a high variance, but it had a very low bias. And then the degree 1 and 2 models could not achieve low bias. They could not fit the training data well, but they don't really vary much when we looked at different sets of training data. So that basically led to overfitting and underfitting. And ideally, we would like to achieve low expected error, so just right. So that means we need to choose the right model expressiveness to achieve both small bias as well as small variance. Okay, so you hear these terms quite a bit, right? Overfitting and underfitting, but more precisely, overfitting means that we have a low bias and high variance. Underfitting means we have high bias and low variance. And just right, the ideal case is both low bias and low variance. So how can we avoid overfitting? we talked about three different ways. First, we can reduce the model capacity, for example, reducing the degree of polynomial features, or in the case of neural networks, we can reduce the number of hidden units in neural networks. We can also add regularizers or increase the regularizer strength, for example, the lambda parameter in ridge regression. In the case of training neural networks, we can also consider early stopping. So we keep track of both the training loss and the validation loss, and we stop training when the validation loss starts to increase. So that gives us a pretty high-level overview of machine learning. And then we talked about specific methods for doing machine learning. So the two main classes of machine learning that we looked at were regression and classification. Right, that's kind of the first thing we need to decide when we do machine learning, right? So are we doing regression or classification? So these are the two main types. So how can you tell? If the goal is to predict a value within a continuous interval, then we have a regression problem. So some examples include predicting the stock price, or asking a robot to decide where to move to next, right? So position and velocity are continuous values. We can also predict the temperature of different cities, for example. So all of these are regression problems. If the goal is to predict one of a discrete set of labels, then we have a classification problem. So this means, for example, predicting whether it rains tomorrow, predicting what object is inside the image, or sometimes some problems can be both regression and prediction. For robotics, which is my area of research, sometimes we try to predict where the robot should go next, so that's regression. But sometimes we fix several options for the robot to move to. So we give the robot a discrete set of choices, and then we try to predict one of them. So that's actually a classification problem. Okay, so we talked a lot about regression problems. So for regression, we had two kinds of models. We had the linear regression models and also non-linear regression models. Obviously, depending on the situation, we may be picking different models to do regression. So for example, if you expect the label to be linear in the input, then we should use a linear regression model. If you expect a label to be non-linear in the input, then we can use a non-linear regression model. Okay, a lot of times we actually don't know. So then we can try both and use what we have learned in model selection to select the best model, right? And usually this means that we want to have a better validation loss. So what linear regression models have we learned about? So, well, there are several different ones, but they're actually very, very similar, especially their solutions, as we have seen. So we have the single output linear regression and multiple output linear regression. I guess choosing between these two is pretty easy. It just depends on whether we want to predict a scalar value or whether we want to predict a vector. For single output linear regression, we looked at this very simple linear model, y hat equals w transpose x. And by defining x the right way, this also includes the constant term. The parameters of the model are w, and we looked at, for example, several different loss functions. One of them is the ridge regression loss function, which is given by this expression here. We sum over all the data points of the square loss of each data point plus a regularizer, plus a L2 regularizer. And the optimal parameters can actually be determined using this closed form formula. So this was obtained by setting the gradient of the loss function to 0 and then analytically solving those equations. When lambda equals to 0, we just go back to ordinary least squares. Okay, and when lambda is positive, we have ridge regression. So for testing, it's pretty easy. After we determine W star, we can simply predict y hat by computing W star transpose x. So in ordinary least squares and ridge regression, we have very similar loss functions, and we have the optimal parameters determined analytically as we discussed. And it turned out that this is just the deterministic interpretation of the problem. We also had a probabilistic interpretation of ordinary least squares and ridge regression. So in this case, we considered a probabilistic model where the model output is a normal distribution with mean W transpose X with a variance of sigma squared, where the sigma is the nuisance parameter that we don't necessarily need to determine, right? The most important thing was W. We also had the option of considering a prior on the parameters, and that basically allowed us to encode what kind of parameters we think are more or less likely, perhaps based on prior experience. So for the probabilistic models, we talked about how the maximum likelihood estimate turned out to be the same as ordinary least squares, and the maximum a posteriori estimate turned out to be the same as ridge regression. So now for multiple output linear regression, it turned out that the math is almost exactly the same, except that our output is a vector, and therefore our model parameters must be a matrix, W matrix times X. And for the loss function, we had something very similar to before. Basically, one part that adds up over all the data points, a form of square loss. And then if we wanted to, we can still add some regularization as well. Okay, and then the closed form formula for the W star turned out to be very similar to what we had before, except that again, the weights are a matrix. And for testing, we simply evaluate the model using the optimal parameters that we determined. Okay, so that was kind of the whole discussion about regression and using linear regression models. What about nonlinear regression models? So there are actually two approaches that we talked about for nonlinear regression. So the first approach is to not change too much. We're still going to do linear regression, but instead of doing linear regression on the raw data points, we're going to do it on the features. The second option is to directly use nonlinear least squares, which uses a model that is nonlinear in the parameters. And there are pros and cons to each approach. For linear regression on the features, we can use the same optimization method as in linear regression. And this optimization method is the simplest that we have. We basically analytically compute the optimal parameter and we get a closed form formula. So that is the biggest pro. What about the cons? Well, one of the cons is that the features are fixed. So we have to know what features to pick, or we have to try many different features. In general, given some fixed features, the model can be less expressive. Sometimes we would like to pick a very high dimensional feature to make the model more expressive, but then the problem becomes more computationally expensive to compute. On the other hand, for nonlinear least squares, some of the pros include that we can actually directly learn the features. So that was the case with the multi-layer perceptrons and neural networks in general. So the model can be more expressive. We don't really need to pick any fixed features. And because we're learning the features, we don't necessarily need to use high dimensional features for the model to be expressive. And the biggest con, and this is a huge con, is that with nonlinear least squares, we can no longer obtain a closed form formula. And even worse, the loss function is actually non-convex. So even with iterative optimization methods, which are needed to solve these problems, we may not be able to find a global minimum. At best, we can only hope for a local minimum. So in linear regression on features, we replaced the raw data points x with phi of x. So our model basically looks almost exactly the same as linear regression on the raw data points. We just replace x with phi of x, and then all the loss function expressions carry through with that replacement. And similarly, this carries all the way to the optimal parameter expression. And we, through using features, polynomial features, we also studied in detail what overfitting and underfitting means, and we explored model selection as well. So one common example that we looked at was the polynomial features of degree up to 2, and this was the expression. So don't forget the cross terms. With higher degree, we have a more expressive model, which is more prone to overfitting. And the lower degree means less expressive and less prone to overfitting. But we could get into underfitting in the first case, for example. For non-linear least squares, we use the model that can be nonlinear in the parameters. And in general, we write that as y hat equals some general nonlinear function f of x with parameters w. The loss function can be very similar as before, the square loss with potentially some L2 regularization. And now, because we can no longer obtain the optimal parameters analytically, we have to use iterative gradient-based optimization algorithms that minimizes the loss function with respect to w. And again, after we do that, for testing is always the same. We evaluate the function f using the optimal parameters that we determined. One linear model that is very popular and that we have covered in detail in this class was neural networks. So I guess one of the takeaways, if you're very new to machine learning, is that there's nothing special about neural networks. Neural networks are just some function f. And we have discussed exactly what this function is. The motivation here was that with neural networks, we can actually learn the features instead of picking the features. And the way we did that was to basically start with the multiple output linear regression model, and we took many steps to say that, okay, instead of x, we're going to replace that with psi of x, but then we want the function psi to have some parameters w multiplied by x. And then after repeatedly doing this, we obtain this model, which is wl times psi of wl minus 1 times the next learnable feature, which is psi of wl minus 2 times the next learnable feature, and so on, all the way down to psi of w0x. And now the parameters are all of these weight matrices, also including biases in there, wl minus 1, and so on, down to w0. Within the function psi, we have nonlinear activation functions. So we really need the nonlinearity, because otherwise the entire neural network with many layers will just collapse down to a single layer. So how do we train neural networks? They lead to loss functions which are nonlinear in the parameters. So of course, no closed form solution in this case. So therefore, we have to train neural networks using iterative gradient-based optimization methods. Because the gradients need to be computed very, very often, and there are many, many parameters, we need to be able to compute gradients efficiently. And this is done using backpropagation. Backpropagation involves the forward pass, which computes all of the activations and pre-activations in every layer. And then afterwards, we perform the backward pass, which computes the gradients with respect to all the variables, including all the weights, as well as the intermediate layers. The loss function, again, is non-convex, so we may not be able to find the global minimum. The most basic algorithm for iterative optimization is gradient descent. And again, gradient descent may get stuck at a local minimum, so there are more advanced variants like momentum, which can sometimes avoid this, but is not guaranteed to do so. We talked about several of these algorithms, including Adam, AdaGrad, and so on. With neural networks, we have done a lot of math on the expression of the gradient and discussed how the gradient of the loss function may vanish or explode. And we talked about several different ways of avoiding these issues. For example, to avoid vanishing gradients, we can use non-saturating activation functions such as ReLU and SoftPlus. We can perform proper initialization of the weights, perform layer normalization, reparameterization, and we can use residual connections. To avoid exploding gradients, a proper initialization, for example, the Xavier and He initialization can also help. Same with layer normalization. We also discussed weight decay and gradient clipping as other options, and it turned out that weight decay is actually the same as L2 regularization. So why neural networks? Well, one of the motivations was that we wanted to learn the features instead of directly picking fixed features. Another motivation is the expressiveness of neural networks, and we have shown that even a neural network with sufficiently many hidden layers, a neural network with just one layer and sufficiently many hidden units in that hidden layer is actually a universal function approximator. It can approximate any continuous function to an arbitrary precision. And we did one example to show exactly that. In general, more hidden units and more hidden layers will give us more expressive neural networks. So with so many parameters, very often we need to watch out for overfitting, and the simplest way is to reduce the expressiveness. So use fewer hidden units, fewer hidden layers. We can also use some of the previous techniques we talked about, such as weight decay and early stopping. So all of that was about regression. And towards the end of the class, we were looking at classification. Okay, so for classification, we also had the choice of choosing linear or nonlinear classifiers. So a linear classifier would be good if the data from different classes can be mostly separated by hyperplanes. Otherwise, we should use a nonlinear classifier. Okay, so we began with the discussion on linear classifiers, and there are two general types: binary linear classifier and multinomial linear classifier. The choice is pretty obvious. If you have two classes, use binary. If you have more than two, use multinomial. So we focused mostly our discussion on binary linear classifier, and the model we chose to take a deeper look at is the support vector machine. So if our data points can be separated, perfectly separated, then we should use the hard margin SVM. Otherwise, we have several choices. We can use the soft margin SVM or logistic regression. So now, if you don't know what to use, you can always try maybe hard margin SVM first. If it's infeasible, then you can switch to one of the other two. Okay, so the most basic version of this is the hard margin SVM. And the goal of hard margin SVM is to find a hyperplane that perfectly separates the positive and the negative data points. And there could be multiple hyperplanes that performs this, but we would like to choose the hyperplane with the highest margin. And the margin is basically the buffer zone on either side of the hyperplane that has no data points. So we like this hyperplane because it provides maximum robustness to perturbations to the data points. So this should lead to better generalization. So then we looked at the optimization problem for hard margin SVM, and we also showed that strong duality holds. So then we derived the dual form. So here are the primal and dual forms. Both the primal and dual forms took many steps of math to derive, so make sure you know all the steps. After defining the dual form of the SVM problem, we looked at how to solve it. Basically, we kind of glossed over how to obtain lambda star, but well, that's basically by solving this dual form of the SVM using some solver. After we obtain lambda star, we can then obtain W star and B star using these expressions. And we saw some nice interpretations for these expressions using complementary slackness. Basically, the mathematical solution agrees with our intuition related to support vectors and margin maximization. After we obtained a model, we did some simple thresholding to perform testing. So y hat simply equals to 1 or minus 1, depending on whether W star transpose xi minus b is greater than or less than 0. In general, we can directly solve the primal problem, or we can do what we did in class. So how do we decide? From a computational perspective, initially it looks like when little n, so this is the dimensionality of x, is much less than the number of data points, then it looks like it's more efficient to solve the primal problem. And otherwise, it's more efficient to solve the dual problem. Okay, but we also saw that the dual problem allowed us to use a kernel trick. So we're going to talk about that in a little bit later. Okay, so what if the data points cannot be perfectly separated? Then we can use soft margin SVM or logistic regression. Again, we took many mathematical steps to derive the loss function for the soft margin SVM, and that turned out to be an unconstrained problem with an objective that was in the form of min over W of sum over some L function over the data points, plus some regularizing term. In both the soft margin SVM case and the logistic regression case, our model was just W transpose X. So the main difference is that this loss function is different. For soft margin SVM, we actually had the hinge loss in green, whereas for the logistic regression, we had this logistic loss in orange. Both of these loss functions are surrogate losses to the 0,1 loss, which is really ultimately what we want to minimize. But the 0,1 loss is actually intractable to minimize. Okay, and then we also compared all of these loss functions with the square loss, and we decided that okay, maybe this is not a good idea for classification because it will over penalize both the correct samples that are too correct or too incorrect. So that's why it's not robust to outliers. And we saw that with the comparison of kind of the decision boundary with the square loss versus the decision boundary with the logistic loss. We can see that in the square loss, all of these outliers are kind of shifting the decision boundary quite a bit. So all of that was about linear classifiers. So what about nonlinear classifiers? So of course, we should use these when the data cannot be separated by a linear hyperplane. We took the same idea from regression, where we replace each data point x with a feature of the data point. And with SVMs, we talked about kernelization. So in this case, we used the kernel trick to avoid expensive computations. So we were able to have high dimensional fixed features, including infinite dimensional fixed features, without much computation by using the kernel trick. So the pros to kernelization is that we can use the same training procedure as for linear classifiers. And the loss function is often convex in Lipschitz, so we can reliably find the global minimum. And the con is that the features are fixed, so the model may be less expressive. On the other hand, we can also use neural networks, which simply take as input low dimensional kind of the raw data points in hopefully a pretty low dimension, and then we learn the features. So the pros are that the features are learned, so the model can be more expressive. But the big con here, as with regression, is that the loss function becomes non-convex, so we may not be able to find the local minimum. So when we use features, we still need to choose what linear classifier to use with the features. And the three choices we talked about were hard margin SVM, soft margin SVM, and logistic regression. For hard margin SVM, we can derive the dual problem, and then it turned out that the dual problem only involves inner products between the data points. So when we replace the data points with features, we can apply the kernel trick. The con is that in hard margin SVM, we have a constraint problem, so we cannot simply use the relatively simple gradient-based optimization methods. For soft margin SVM, we can also derive the dual, and it also involves only the inner products between the data points. So the kernel trick can be applied here as well. However, the con is that the iterative gradient-based methods may not work so well because the derivative of the hinge loss is discontinuous. So the third option is logistic regression. So the con is that the pro is that we can use iterative gradient-based methods for optimizing the loss function. However, we cannot apply the kernel trick. Okay, so I guess another way of putting it is that hard margin SVM works with kernelization, but not with neural networks. And that's also true with soft margin SVM. It turns out that soft margin SVM can work a little bit with neural networks. In fact, we do that in our research in robotics when we try to classify whether the robot is safe or not. For logistic regression, it works well with neural networks, and it does not work with kernelization. Okay, so we delve into a lot of math related to hard margin SVM with kernels. We talked about how different kernels are related to different features. And some of the most popular kernels are the linear kernel, which corresponds to simply the raw data points being the features themselves. We talked about the quadratic kernel and also the polynomial kernel, which correspond to quadratic features and polynomial features. We also looked at the example of the radial basis function kernel, where the kernel is easy to compute, but it turned out that the corresponding features were actually infinite dimensional. For logistic regression with neural networks, we use, the model is a neural network where the output layer has a sigmoid activation function so that the output gets squashed to between 0 and 1. As with regression with neural networks, the parameters are the weight matrices in all the layers. But where it differs from regression is that the loss function we use is typically going to be the cross entropy loss, not the square loss. We can train the neural network using this gradient-based optimization methods. And for testing, we do some simple thresholding on the sigmoid function. So how do we get to discussing all of these concepts? All of these concepts are built on the foundation of strong mathematics. And the math topics that are really important that we use throughout the course include linear algebra, where we talked about the singular value decomposition, the eigendecomposition, and their relationships. In particular, we related the right and left singular vectors to the eigenvectors of kind of this symmetric matrix form. And then we also talked about the non-singular values and how they relate to the eigenvalues. We talked about different norms. We had the vector norms, which hopefully most of you were already familiar with, but there were some norms for matrices, for example, the Frobenius norm, as well as the induced 2 norm for matrices. And that turned out to be the same as the larger singular value of A. So we also talked about the positive definiteness of matrices using 2 equivalent definitions, one based on the eigenvalues, another based on whether the associated quadratic form is always non-negative. We saw that in the special case of a matrix in the form of A transpose A, that matrix is always going to be positive semi-definite. Besides linear algebra, we also talked a lot about calculus. We talked about convex definitions and the two equivalent definitions of it. The first one being a line segment across any 2 points must lie on or above the surface. We also looked at a second order definition, which is that the Hessian of the function must be positive semi-definite everywhere. And this discussion was very important because it allowed us to analyze, characterize critical points of the loss function. So when a function is convex, every critical point is a local minimum, and every local minimum is a global minimum. To perform many of the derivations we did in class, we used matrix derivatives, product rules for inner products, for example, and the sum rule and kind of the derivative of the quadratic form. So hopefully this course gave you a fundamental understanding of the basic machine learning algorithms, as well as the associated optimization problems and how we can solve them. Hopefully you also got a good refresher on the math needed for machine learning as well. So after this course, there are many advanced courses that I can recommend. So in the area of core machine learning, we can consider CMPT 727, Statistical Machine Learning. So that course focuses more on probabilistic models. There's also CMPT 728, which is deep learning. In that course, we analyze more about neural networks. So we have a more in-depth discussion on neural networks. And Professor Curley also teaches CMPT 983, which is a special topics course on deep generative models. So models for generating complex data such as images, text, videos, and so on. There are also many courses on the applications of machine learning, such as CMPT 762, taught by Yasu Furukawa. So this course uses advanced neural networks for extracting information from images. There's also CMPT 720, robotics course, the robotics course that I teach. So this course covers classical and data-driven methods in robotic systems. And lastly, we have CMPT 825, natural language processing, taught by Professor Angel Chang. So this course looks at machine learning methods for extracting information from text. So that finally concludes CMPT 726, machine learning. I hope all of you guys were able to take away something useful, and I'll see you guys in other courses or in research labs.